Hello everyone, welcome back. I'm your friend in So today we're going to learn the polynomial graphs. Zeros of polynomial introduction. What is that? What is the zeros of polynomials?
Zeros of polynomials.
Let's say that we have a polynomial p of x, and we can factor it, and we can put it in the form x minus 1 times x plus 2 times x minus 3 times x plus 4. And what we are concerned with are the zeros of this polynomial. And you might say, what is a zero of a polynomial? Well, those are the x values that are going to make the polynomial equal to 0. So another way to think about it is, for what x values is p of x going to be equal to 0? Or another way you can think about it is, for what x values is this expression going to be equal to 0? So for what x values is x minus 1 times x plus 2 times x minus 3 times x plus 4 going to be equal to 0. I encourage you to pause this video, think about that a little bit before we work through it together. Well, the key realization here is if you have the product of a bunch of expressions, if any one of them is equal to 0, it doesn't matter what the others are because 0 times anything else is going to be equal to 0. So the fancy term for that is the zero product property. But all it says is, hey, if you can find an x value that makes any one of these expressions equal to 0, well, that's going to make the entire expression equal to 0. So the zeros of this polynomial are going to be the x values that could make x minus 1 equal to 0. So x minus 1 equals 0. Well, we know what x value would make that happen if x is equal to 1. If you add 1 to both sides here, x equals 1. So x equals 1 is a zero of this polynomial. Another way to say that is p of 1, when x equals 1, that whole polynomial is going to be equal to 0. How do I know that? Well, if I put a 1 in right over here, this expression right over here, x minus 1, that is going to be equal to 0. So you're going to have 0 times a bunch of other stuff, which is going to be equal to 0. And so by the same idea, we can figure out what the other zeros are. What would make this part equal to 0? What x value would make x plus 2 equal to 0? Well, x equals negative 2. X equals negative 2 would make x plus 2 equal 0. So x equals negative 2 is another 0 of this polynomial. And we could keep going. What would make x minus 3 equal to 0? Well, if x is equal to 3, that would make x minus 3 equal to 0. And that would then make the entire expression equal to 0. And then last but not least, what would make x plus 4 equal to 0? Well, if x is equal to negative 4. And just like that, we have found 4 zeros for this polynomial. When x equals 1, the polynomial is equal to 0. When x equals negative 2, the polynomial is equal to 0. When x equals 3, the polynomial is equal to 0. And when x equals negative 4, the polynomial is equal to 0. And one of the interesting things about the zeros of a polynomial, you could actually use that to start to sketch out what the graph might look like. So for example, we know that this polynomial is going to take on the value 0 at these zeros. So let me just draw a rough sketch right over here. So if this is my x-axis, that's my y-axis. That's my y-axis. And so let's see, at x equals 1, so let me just do it this way. So we have 1, 2, 3, and 4. And then you have negative 1, negative 2, negative 3, and then last but not least, negative 4. We know that this polynomial, p of x, is going to be equal to 0 at x equals 1. So it's going to intersect the x-axis right there. It's going to be equal to 0 at x equals negative 2, so right over there. At x equals 3, right over there. And x equals negative 4. Now, we don't know exactly what the graph looks like just based on this. We could try out some values on either side to figure out, hey, is it above the x-axis or below the x-axis for x values less than negative 4? And we can try things out like that, but we know it intersects the x-axis at these points. So it might look something like this. This is a very rough sketch. It might look something like this. We don't know without doing a little bit more work. But ahead of time, I took a look at what this looks like. I went on to Desmos and I graphed it. And you can see it looks exactly as what we would expect. The graph of this polynomial intersects the x-axis at x equals negative 4. Actually, let me color code it. X equals negative 4, and that is that 0 right over there. X equals negative 2, that's this 0 right there. X equals 1 right over there. And then x equals 3 right over there. In future videos, we will study this in even more depth.
Alright, at least we Now we know what is the zeros of polynomial. It's not a fancy word. It's just about what the x value which would make the entire equation equal to 0. And as you know, in China, those teachers would likely to try to tell you what's a row that makes the line in the upper side of the axis or the lower side of the axis. But in here, what he just said is that you don't know whether that line would go from up or would go in from the bottom side. But you could try some value to get to know whether that line was going in from upper side or the lower side.
We're told we want to find the zeros of this polynomial, and they give us the polynomial right over here, and it's in factored form. And they say plot all the zeros, or the x-intercepts, of the polynomial in the interactive graph. And so this is a screenshot from Khan Academy. If you're doing it on Khan Academy, you would click where the zeros are to plot the zeros, but I'm just going to draw it in. So pause this video and see if you can have a go at this before we work on this together.
So again, he just said that we need to walk through this before he teach us. So this is basically what we have. If we want to draw out the graph of this, first we need to have an empty axis graph, something like this. Yeah, still remember how to do this. Then after that we need to calculate out the 0 point of this equation. So as far as I say, the x could be equal to 0 and 2x plus 3 could be equal to 0. And from this equation, we could get that 2x might equal to negative 3. Then the x could be equal to negative 3 over 2. And that's the second 0 point. Then the x minus 2 could be equal to 0. And for this case, the x would be just equal to 2. Alright, so now we got all those 0 points. It could be equal to 0, and it could be equal to 1, 2, it could be equal to x equal to 2, and it could be equal to negative 3 over 2, which is this point. Okay, then how do we know the line, whether it's in the upper side or it's in the lower side? How do we know that? Well, we didn't know unless we test it out. For example, now if we assume the x equal to 1, then the px, what it would be? It's equal to 2 times 2 plus 3 and 1 minus 2, which is equal to 10 times negative 1 equal to negative 10. Alright, so it would be start from the lower side. So for this one, that'll be something like this. Then how about this side? Whether it's coming from the upper side or the lower side? Well, we don't know unless we put the negative 1 into it. So that'll be negative 2 times negative 2 plus 3 times negative 1 minus negative 2, and it's equal to 1 times negative 2 times the negative 3. In the end, it's equal to 6. So it's a positive number. Then that means for the interval from negative 3 over 2 to the 0, the graph should be in the upper side. Then for the rest of the part, we just have to add some lines into it. So the final result for this graph would be just something like this. We don't know, but let me just I'll just put this one into the top of the screen. Then I'm going to continue to watch the video.
All right, now let's work on this together. So the zeros are the x values that make our polynomial equal to 0. So another way to think about it is, for what x values are p of x equal to 0, those would be the zeros. So essentially we have to say, hey, what x values would make 2x times 2x plus 3 times x minus 2, because this is p of x, what x values would make this equal to 0? Well, as we've talked about in previous videos, if you take the product of things and that equals 0, if any one of those things equals 0, at least one of those things equals 0, it'd make the whole product equal to 0. So for example, if 2x is equal to 0, it would make the whole thing 0. So 2x could be equal to 0, and if 2x is equal to 0, that means x is equal to 0. And you could try that out. If x is equal to 0, this part right over here is going to be equal to 0. It doesn't matter what these other two things are. 0 times something times something is going to be equal to 0. And then you could say, well, maybe 2x plus 3 is equal to 0. So we could just write that. 2x plus 3 is equal to 0. And if that were true, what would x have to be in order to make that true? Subtract 3 from both sides. 2x would have to be equal to negative 3, or x would be equal to negative 3 halves. So this is another x value that would make the whole thing 0. Because if x is equal to negative 3 halves, then 2x 2x plus 3 is equal to 0. You take a 0 times whatever this is and whatever that is, you're going to get 0. And then last but not least, x minus 2 could be equal to 0. That would make the whole product equal to 0. So what x value makes x minus 2 equal 0? We'll add 2 to both sides, and you would get x is equal to 2. If x equals 2, that equals 0. Doesn't matter what these other two things are. 0 times something is going to be equal to 0. So just like that, we have the zeros of our polynomial. And the reason why they have x-intercepts in parentheses here is that's where the graph of p of x, if you say y equals p of x, that's where it would intersect the x-axis. And that's because that's where our polynomial is equal to 0. So let's see, we have x equals 0, which is right over there. Once again, if you were doing this on Khan Academy, you would just click right over there and it would put a little dot there. We have x is equal to negative 3/2, which is the same thing as negative 1/2. So that's right over there. And then we have x equals 2, which is right over there. So those are the x-intercepts, or the zeros, of that polynomial. Now, this is useful in life because you could use it to graph a function. I don't know exactly what this function looks like. Maybe it looks something like this. Maybe it looks something like this. We would have to try out a few other values to get a sense of that, but we at least know where it's intersecting the x-axis. It's at the zeros.
So in the end, he didn't actually drawing out the whole graph, but instead he just put some points into the x-intercepts or the x-axis. He didn't do the whole stuff. Alright, then let's get into the next part. Positive and negative intervals of polynomial. What is that?
Let's say that we have the polynomial expressed in factored form. It is x plus 2 times 2x minus 3 times x minus 4. What we're going to do in this video is use our knowledge of the roots of this polynomial to think about intervals where this polynomial would be positive or negative. And the key realization is that the sign of a polynomial stays the same between consecutive zeros. Let me just draw an arbitrary graph of a polynomial here to make you appreciate why that is true. So x-axis, y-axis. And if I were to draw some arbitrary polynomial like that, you can see that between consecutive zeros, the sign is the same. Between this 0 and this 0, the polynomial is positive. Between this 0 and this 0, the polynomial is negative. And that's almost intuitively true because if the sign did not stay the same, that means you would have to cross the x-axis. So you would have a 0, but we're saying between consecutive zeros. So between this 0 and this 0, it is positive again. Then after that 0, it stays negative. Once again, the only way it wouldn't stay negative is if there were another 0. So now let's go back to this example here, and let me delete this because this is not the graph of p of x, which I have just written down. Let's first think about its zeros. So the zeros...
Alright, here guys, we got another sentence example. I have just written down. So if you just somehow write some code, you could say, oh, the code I have just written down. Or you would say some content, some sentence, or some objects. Then you say, which I have just written down. That's a sentence.
P of x, which I have just written down. Let's first think about its zeros. So the zeros are the x values that would either make x plus 2 equals 0, 2x minus 3 equals 0, or x minus 4 equals 0. So first, we can think about, well, what x values would make x plus 2 equal to 0? Well, that, of course, would be x equals negative 2. What x values would make 2x minus 3 equals 0? 2x minus 3 equal to 0. Add 3 to both sides, you get 2x equals 3. Divide both sides by 2, you get x equals 3/2. And then last but not least, what x values would make x minus 4 equal to 0? Add 4 to both sides, you get x is equal to 4. And so if we were to plot this, it would look something like this. So this is x equals negative 2, x equals negative 1. This is 0. This is 1, 2, 3, and 4. Let me draw the y-axis here. So the y-axis would look something like...
Okay, it reminds me something. So actually we don't have to draw the vertical line, which is the y-axis at the first. We could actually draw the x-axis first, then put those numbers in, because we know what those x values that we really need. For example, here it's the value from negative 2 to the positive 4. So we could draw those values first before we draw the vertical y-axis. But for me, back in the school, I always like to draw the x-axis and y-axis first, then put those numbers in. But that makes sense because you don't know where the y-axis should be put in at the first, unless you draw the x values first.
Like this, x and y. We have a 0 at x equals -2, so our graph will intersect the x-axis there. We have a 0 at x is equal to 3/2, which is 1.5, which is right over there. And we have a 0 at x equals 4, which is right over there. And so we have several candidate intervals. And actually, let me write this down in a table. So the intervals over which, and this is really be between consecutive zeros, intervals to consider. I'll draw a little table here. So you have x is less than -2. That's one interval. X is less than, actually, let me color code this. So if I were to say the interval for x is less than -2, so that's this yellow that I draw at the extreme left there, we could have an interval where x is between -2 and 3/2. So -2 is less than x is less than +3/2. That would be this interval right over here. You have the interval, I'm trying to use all my colors, between 3/2 and 4, this interval here. So that would be 3/2 is less than x is less than 4. And then last but not least, you have the interval where x is greater than 4, that interval right over there. So x is greater than 4. Now, there's a couple of ways of thinking about whether over that interval our function is positive or negative. One method is to just evaluate our function at a point in the interval. And if it's positive, well, that means that whole interval is positive. If it's negative, that means that the whole interval is negative. And once again, it's intuitive because if for whatever reason it were to switch, we would have another 0. I know I keep saying that. But another way to think about it is, over that interval, what is the behavior of x plus 2, 2x minus 3, and x minus 4? Think about whether they're positive or negative and use our knowledge of multiplying positives and negatives together to figure out whether we're dealing with a positive or a negative. So let's do it. We can do it both ways. So let's think of this as our sample x value. And then let's see what we can intuit about or deduce about whether over that interval we are positive or negative. So for x is less than -2, maybe an easy one or an obvious one to use. It could be any value where x is less than -2. But let's try x is equal to -3. So you could try to evaluate p of -3. You could just evaluate that. Actually, let's just do that. So that's going to be equal to -1 times 2 times -3 is -6 minus 3 is -9. -9 times -3 minus 4, that is -7. So if you were to multiply all of this out, this would give you -63, which is clearly negative. So over this interval right over here, our polynomial is going to be negative. So then we can move on to the next one. And an interesting thing is we didn't even have to figure out the 63 part. We can just see that there's a negative times a negative times a negative, which is going to be a negative. And so let's just do that going forward. Let's just think about whether each of these are going to be positive or negative and what would happen when you multiply those positive and negatives together. Now in this second interval between -2 and 3/2, what is going to happen? Well, we could do a sample point. Let's say x is equal to 0. That might be pretty straightforward. Well, when x is equal to 0, we're going to be dealing with a positive times a negative times a negative. A positive times a negative times a negative. And the reason why I did that, I just did in my head. I said, okay, that's going to be a +2 times a -3 times a -4. So positive times a negative times a negative. So I could write it this way. It's going to be a positive times a negative times a negative. Well, a negative times a negative is a positive, and a positive times a positive is a positive. So we are positive over that interval. And if you were to evaluate p of 0, you will get a positive value. Now, what about this next interval? What about this next interval here between 3/2 and 4? We could try x is equal to 2. When x is equal to 2, we are going to get a positive times a positive times a 2 minus 4 is negative times a negative. So this is going to be negative over that interval. And then last but not least, when x is greater than 4, we could try x.
Alright, so from this example, or by using this kind of strategy, we could do it very quickly without much thinking. For example, now, if he said the x must greater than 4, then we could say, well, how about x equal to 5? Okay, if x equal to 5, the first one would be positive for sure, and the second one would be also positive. And the third one, since it's 5 minus 4, that would be 1, so it's also positive. So in the end, we got a, let's say, positive value in that interval. And that indeed makes sense because at the first, it's start from the negative, then it goes in positive, and it goes in negative, then it goes in positive again. It seems like the negative and the positive is always switching around in this case.
Is equal to, let's say, 5. We are going to have a positive times a positive times a positive. So we are going to have a positive. And as I mentioned, you could also do it without the sample points. You can say, okay, when x is greater than 4, you can say, okay, for any x greater than 4, if you add 2 to it, that for sure is going to be positive. For any x greater than 4, if you multiply it by 2 and subtract 3, well, that's still going to be positive because 2 times something greater than 4 is definitely greater than 3. And for any x greater than 4, if you subtract 4 from it, you're still going to have a positive value. So that's another way to think about it.
Alright, that's enough for this video. So let's go to another one. Here's a word called multiplicity. What is that?
All right, now let's work through this.
Multiplicity.
Multiplicity. Alright. Zeros of multiplicity. Oh, that's let me just go through that video. I don't know why, but it seems like the Khan Academy was trying to use their own video player than the YouTube, and their own video player is quite bad since it won't see my audio value everywhere. So for each time I have to manually adjust this value over and over again, which is quite bad.
Together, and we can see that all of the choices are expressed as a polynomial in factored form. And factored form is useful when we're thinking about the root polynomial, the x values that make that polynomial equal to 0. The roots are also evident when we look at this graph here. We have a root at x equals -4, a root at x equals -1.5 or -3/2, and a root at x is equal to 1. So really what we have to do is say which of these factors are consistent with the roots that we see. So let's go root by root. So here on the left we have a root at x equals -4. In order for this polynomial to be 0 when x is equal to -4, that means that x plus 4 must be a factor, or some multiple or some constant times x plus 4 must be a factor of our polynomial. Now we can see in the choices that we have a bunch of x plus 4s, but they have different exponents on them. The first one has a 2 as an exponent, it's being squared, while the others have a 1 as the exponent. Now what we've talked about in other videos when we talked about multiplicity, we said, hey, if we see a sign change around a root, like we're seeing right over here around x equals -4, that means that we are going to see an odd exponent on the corresponding factor. But if we didn't see a sign change, as we see in this other root over here, that means we would see an even exponent. Now, we clearly see the sign change, so we would expect an odd exponent. And of course, 1 is an odd number and 2 isn't. So if you just have a straight up x plus 4, you would have a sign change around x equals -4. So I can rule out this first choice. These other 3 choices are still looking good based on just the x plus 4 factor. Now let's move on to the next factor right over here. Or the next root. The next root is that x is equal to -3/2. And so one way to think about it is you could have a factor that looks like x plus 3/2, or this times some constant. Now, when we look at the choices or the remaining choices, we don't see x plus 3/2, but we do see something that involves a 2 and a 3. And so one way to think about it is hey, if I just multiply this times the constant 2, so that would get us 2x plus 3. Well, I do see that right over here. And then the next question is, what should be the exponent? Well, once again, we have a sign change around x equals -3/2. So we would expect an odd exponent there. And you can see out of the choices, only 2 of them have an exponent of 1.
Alright, here he just said a word called odd. Okay, this is a very important concept in mathematics. So for the odd, what is the odds number? Well, it's some number like 1, 3, 5, 7. They are those numbers that cannot be divided by 2 to get an integer. But there's another types of numbers. It's called even. And for even number, it could be just like, numbers like 2, 4, 8, 12, or maybe 10 inside of it. So these numbers, they are even because they could be divided by 2. For example, 4 divided by 2 would be equal to an integer. So any numbers that can be divided by 2 and get an integer back, then we call it an even number. For this case, it is said that if the sign of this cross line changed after he goes through the 0 points, for example, in here it's a positive value, but when this line goes into here, it becomes a negative value. So that means the sign has been changed. And for this case, that factory, let's say the exponent of that factory is an odd number. Why? Because as we all know, if we got a negative number, and if we give it an even value, for example 2, the result would be a positive value. But if we have a negative value and we got an odd exponent, for example, if we got 1, it's an odd exponent value, right? Then the result would be still a negative value, so the sign didn't change. But if a number have an even exponent, then the sign would be changed. It will be changed from a negative value to positive value. Yeah, but it seems like it has nothing to do with current situation, because for now, right here, it says that clearly when the exponent is odd, then the sign would be changed. Yeah, how to think about this? Well, if we say we got express like this, x minus 2, and we got an even exponent for it, for example 2, then whatever value inside of it, whether it's positive or negative, the result would always be positive. The result would be always positive. So that's the case right in here. No matter what kind of value you give to me, it will always be the same sign as the output. But for the odd exponents, that can be quite tricky. So for the x plus 4, if it's a negative value, then the output is a negative value, and if it's a positive value, the output is a positive value. So that's why the sign gets changed from positive to negative after the line going through this 0 points. I hope I explain it very well.
1, which is an odd number, while the other one has an even exponent there. So we can rule that one out as well. And then we go to this last root. I will do this in an orange color. We have a root at x equals 1. So we would expect x minus 1, or this multiplied times some constant, to be one of the factors. And what's interesting here is we don't see a sign change around x equals 1. So we would expect an even exponent. And so out of the remaining choices, we see an x minus 1 in both of them, but only choice C has the even exponent that we would expect. So choice C is looking good. If we were to go with choice D, where this is to the first power, we would expect a sign change around x is equal to 1. So this would be a situation where the curve would keep going down, something like that. So we like choice C. Let's do another example. So once again, we are at...
And if we keep thinking about that, let's say if we got an x minus 2 as the expression, and it has an exponent of 2. Why? I would say the value x minus 2 would be either positive or negative. Well, simply because when this point going through a 0 point, why we call it 0 point? Because the numbers has to go through the 0 point, and when he goes through it, either the line would be either from, in this case, from negative, the x value would be go from the negative to positive, or it will be go from the positive to negative, because that's the 0 points. Numbers between the 0 would be either negative or positive. There is in the between of two of them.
That's what could be the equation of P, and we're given a graph. So again, pause this video and try to work through that. All right, we're going to do the same idea. Let's go to this first root right over here. We have a root at x equals negative 3. So we would expect some multiple of x plus 3 to be one of the factors. We also have a sign change around x equals negative 3. So we would expect an odd multiplicity, and we would expect an odd exponent on the x plus 3 factor. When we look at all the choices, C and D have an even exponent. So if we had x plus 3 to the 4th, then you wouldn't have a sign change here. You would just touch the x-axis and then go back to where it was coming from. So we can rule out these choices. And now let's look at the second root right over here at x is equal to 2. So we would expect x minus 2 to be one of the factors, or a multiple of this. And because we don't have a sign change around x equals 2, the graph just touches the x-axis and then goes back to where it was coming from, we would expect an even exponent here. And so when we look at the choices around the x minus 2 factor, we see only one of them has an even exponent. So I am liking choice B, and we are done.
Right, here we got another section, end behavior of polynomials. What is that? Why do you call it end behavior?
Polynomial end behavior. And this is really just talking about what happens to what I want to do in this video is talk a little bit about polynomial end behavior. And this is really just talking about what happens to a polynomial if as x becomes really large or really negative. For example, we're familiar with quadratic polynomials where y is equal to ax squared plus bx plus c, we know that if a is greater than 0, this is going to be an upward opening parabola of some kind. So it's going to look something like that, the graph of this equation or of this function, you could say. And if a is less than 0, it's going to be a downward opening parabola. It's going to be a downward opening parabola. We spent less time with third degree polynomials, but we've also seen those a little bit. So for example, if you have the third degree polynomial, y is equal to ax to the third plus bx squared plus cx plus d. If a is greater than 0, if a is, I don't want to use that brown color, if a is greater than 0, when x is really negative, this whole thing is going to be really negative. And then it's going to increase as x becomes less negative. It's going to do something that might do a little bit of funky stuff in between. But then as x becomes more and more positive, it will become more and more positive as well. So it might look something like this when a is greater than 0. But what about when a is less than 0? Well then, just like here, we would flip it. So let me write this. So if a is less than 0, when x is really negative, you're going to multiply that times a negative a, and you're going to get a positive value. So it's going to look something like this. And then it's going to go like this. It might do a little bit of this type of business in between, but then its end behavior, it starts decreasing again. So when we talk about...
Okay, so when I first look at this graph, it reminds me a lot because those things are what we were been doing back in the school. Try to analyze the features of those equations, as I would say. For example, what kind of the value change in a would affect the whole equation's value? Well, it says that when the x greater than 0, the whole stuff looks like this. It didn't complete its totally. It should be something like this. This is the x-axis for both of the graphs. And as you know, when a is greater than 0, that's obvious because the x squared would always be a positive number. So if you give it a positive number, it's a positive number. If you give it a negative number, it will become a negative number for sure. Now, if you look at this, one, since it's x to the third power, this value x to the third power could be either positive or negative. If you give it a, let's say, negative number, if this is a 0 point, it will be a negative 1. And if you give it a positive number, it will be positive. Was that right? I don't know. I would like to hear what the Kahan would like to teach, why this is something like this. Alright, I guess I could solve this out. So let me do this. At the first we get an integer like this. We will assume it's a positive number, and this is a 0 point. When the whole number goes to the left, the x decreases, but this stuff didn't strong enough to make the whole equation equal to a negative 1. So in this interval from here to here, it's still positive. But when it goes to a limitation point, like this point, this part is definitely greater than this positive integer, or let's say it's less than that. So it makes the whole equation to be a negative number. So that's why you say a negative 1. It's the same thing for the right side. So I won't cover it right in there. Again, let me assume this is the 0 point, or this is where the x equal to 0, and we got the x-axis right in here, and we will still assume this part is a positive number. Then as the x goes to the left, it means the x gets smaller and smaller. This is a negative number since a less than 0. When a negative number meets a negative number, it gets a positive number. But this positive number was not strong enough. So in this interval, it's less than this positive number. So it's probably we'll assume this one is a negative 1. But that's fine. For this part, it's a negative stuff. But when the point comes, when the limits comes, the whole part now becomes greater than this negative number. So in that case, we got a positive number right here. Anyway, it's just my assumption. We could go through the video to say what it really is.
End behavior. We're talking about the idea of what is this function? What does this polynomial do as x becomes really positive, and as x becomes really negative, and kind of, fully recognizing that some weird things might be happening in the middle. But we just want to think about what happens as extreme values of x. Now, obviously, for a second degree polynomial, nothing really weird happens in the middle. But for a third degree polynomial, we see that some interesting things can start can start happening in the middle. But the end behavior for third degree polynomial is that if a is greater than 0, we're starting really small, really low values, and as a becomes positive, we get to really high values. If a is less than 0, we have the opposite. And these are kind of the two prototypes for polynomials, because from there we can start thinking about any degree polynomial. So let's just think about the situation. Let's just think about the situation of a fourth degree polynomial. So let's say y is equal to ax to the fourth power plus bx to the third plus cx squared plus dx plus, I don't want to write e because e has other meanings in mathematics. I'll say plus, well, I'm really running out of letters here, plus even f, I don't want to, I'll just use f, although this isn't the function f, this is just a constant f right over here. So let's just think about what this might look like. Let's think about its end behavior, and we can think about it relative to a second degree polynomial. So its end behavior, if x is really negative, x to the fourth is still going to be positive, and we're going to be, if a is greater than 0, when x is really negative, we're going to have really positive values, just like a second degree. And when x is really positive, same thing. X to the fourth is going to be positive, times a is still going to be positive. So its end behavior is going to look very similar to a second degree polynomial. Now, it might do, in fact, it probably will do some funky stuff in between. It might do something that looks, kind of like that in between, but we care about the end behavior. So this is, I guess you could call the stuff that I've dotted line in the middle, this is called the non-end behavior, the middle behavior. This will obviously be different than a second degree polynomial, but what happens at the ends will be the same. And the reason why, when you square something or you raise something to the fourth power, you raise anything to any even power for very large, as long as a is greater than 0, for very large positive values, you're going to get positive values, and for very large negative values, you're going to get very large positive values. You take a negative number, raise it to the fourth power or the second power, you're still going to get a positive value. Likewise, if a is less than 0, you're going to have very similar end behavior to this case. For a polynomial where the highest degree term is even, so this is a is less than 0, your end behavior, when a is really negative, this thing's going to be really positive. We're going to be multiplying it times the negative, so it's going to be really negative. So it'll look like this. And likewise, when x is really positive, you get the same thing, because you're going to be multiplying a positive times a, which is negative. And in between, it might be doing something, it might do something like that, but its end behavior, you see, is very similar to a second degree polynomial. So if you ignore this, its end behavior is very similar.
All right. So when I say this, one thing start to come into my mind, which is if we want to do some analysis for the end behavior, so in the end, you don't care about those small items inside of a equation or expression. What you really care about is the biggest exponent one, the one that has a biggest exponent. For example, here it's a 3, and here it's a 2, and here it's a 4. Why we only care about that? Because that's the boss for the whole expression. So in the end, only this item could affect the whole expression when the x value bigger enough or smaller enough.
Now, the same is true for a fifth degree if you were to compare it to a third degree. And the overall idea here is what happens to this value when we get really large x's or really small x's? Are we taking it to an even power, in which case for either really negative values or really positive values, we're going to get positive values, and then it depends what our coefficient a is, or are we taking it to an odd power? So the general idea, and actually let me just do a fifth degree just to make it clear. So if I had something of the form y is equal to ax to the fifth plus bx to the fourth plus, and it just went all the way, I won't have to even write.
Okay, maybe then we could explain it in another way after I said that. So it is said that x would be, if we analyze this endpoint, then the x would be getting to smaller and smaller, approaching to negative infinity. And in this case, if the a is a positive number, then the whole expression would be definitely to a negative infinity. But let's say when we analyze it in another situation, when the x goes to, let's say, bigger and bigger, for example this one, this endpoint, then if the a is a positive number, the whole stuff would be a positive, just like this one. Again, it's the same thing for this one. For example, if the x to the third power goes to negative infinity, then it's a negative value, right? But for this case, if the a is less than 0, then two negative number multiple each other will get a positive number. So that's exactly why for this end point, or for this limitation, we got the value, or we got the positive value right in here.
This thing, if a is greater than 0, would look something like this. Its end behavior is very similar, or it is similar to a third degree polynomial where a is greater than 0. At the end, it would do this. Now it might do kind of some craziness. It might do some craziness like this. I have to get this right. So it's 1, 2, 3. It might do some craziness like this in between. But then for really large x's, it will look the same as ax to the third when a is greater than 0. So once again, very, very similar end behavior when a is greater than 0, and very similar end behavior when a is less than 0. It would look like this. At the ends, at a negative value, it will be positive, because this part is going to be really negative, but then it's going to be multiplied by negative to get a positive. And for really positive values of x, it will be negative, because once again, this a term is going to be negative, and then what it does in between, where, at least for the sake of this video, we're not really thinking about. So the big takeaway here, and this is kind of a little bit of a drum roll here when we're talking about end behavior, if you're looking at an even degree polynomial, it's going to have end behavior like a second degree polynomial. If you ignore what happens in the middle, what happens at really negative values of x and really positive values of x is going to be very similar to a second degree polynomial. And if your degree...
Okay, he was over talking about all those stuff. Alright, it seems like we have just finished the whole stuff. From today's learning, we at least know how to draw polynomial graphs. Well, the strategy for us is just first, we need to find out all those 0 points, right? And then we're gonna plot those 0 points into the x-axis. And after that, we do some analyze to get the information about whether the value inside of one of those interval is positive or negative. Once we got that kind of information, we could be able to just connect those points together to form a line. Okay, if you don't know what I was talking about, what I said is just first we need to get all those 0 points. For example, this point, this point, this point. Then we draw the x-axis and y-axis, and we get the information of whether at some interval the value is positive or negative. After that, we form a line. That's it. That's how we draw polynomial graphs. Okay, that's today's learning, and I hope you guys enjoyed it, and I will see you guys in the next video. Bye.